scheduled today as a repeating occurrence. I don't know. So with Ring Central, it wants a link to a calendar. So for me, the calendar that I use is iCal. I don't know how that came across to you guys. You're all here, you were able to log in. I don't know if you need to change that to your calendars or if there's something I can do to add additional calendar types to the invite. I'm not really sure. So that's, I tried doing that. I also contacted the help desk about the recording for the class. I can't find it from last week, and they said it was in my documents folder, and I can't find it in my documents folder. I can't find it in Ring Central. I can't find it with my Outlook through Woodbury. It's not in my downloads. I've emailed them back again. I haven't heard yet of where I'm supposed to look for it. So I don't know. It's going to still be an experiment to try and get these recorded for you guys. So sorry about that. If you guys have it figured out in any other classes or anyone is recording stuff and you have any suggestions, please let me know. The help desk puts me as a low priority. I was not happy to see my email returned with the low priority symbol.
Sorry, what was the thing you were having a hard time recording, or?
Well, last session on Friday, it said that so we recorded the second half of the class, and then when I ended the class meeting and the I guess it's the meeting. Yeah. When I ended that,
you should have been saving the file to your computer.
Right. I don't know where it would be on my computer.
Okay, so when you do it today, you should be able to ask it to open for you, and then at the top of, do you have a PC or do you have a Mac?
I have a Mac.
Okay, so this is going to depend on how you have your Finder window set up, to be honest.
Okay.
Your Finder window, you have settings in your preferences. So you have a an address bar, and it'll actually tell you what files are within what files. So, but you may have turned it off. If you want, I can go over it with you. I'm an ex-computer tech, an ex-Apple computer tech.
How about
I've been recording my sessions for all of last semester because I've got the disabilities thing. You'll be getting my email today from my disabilities coordinator. So if you would like, I spent an entire semester recording these sessions, and I'm an ex-computer tech, so I can help you with this.
That would be so awesome. How about at the end of today, when we're done, we talk a little bit more before hanging up. Okay.
Sounds good.
And maybe there's some places in my Finder windows I can look. So, okay. And then I have hit the record button for this session too. So hopefully that's recording also. So, great. Thank you, Tabitha. I appreciate that. Okay. So recording, and then the recurring meetings. So the one I set up so far is just for Tuesdays. I think I'll do another one for Fridays. And if you aren't getting the invites or the email or something, let me know. Did today's invite come from my personal email address? It would have been katie@me.com or Katie.
Yeah,
2633.
So we got it in our Woodbury email. It came in as from your regular email. It won't, since we're in Outlook, our school Outlooks are not linked to any of our personal iCals, and only some of us have been able to get our school Outlook to work consistently on our devices. So many of us can't really add to the calendar. If anything, we can create our own event in our own calendars, but it won't let it sync with Outlook, basically.
Well, I was a little disappointed when I did find it and link it to my calendar. It still doesn't show up in my Ring Central app. When I open that, it doesn't say I have something scheduled, which is like super annoying. And I already have it on my personal calendar.
You probably have to link your iCal with Ring Central's calendar function if it has such a thing. I don't know if it does because they give you teachers a different, basically different access than they give us students. So I don't have all of the capabilities in Ring Central that you would have as a professor. So I don't know how to do that.
I tried that. They only have two different calendars to link to. It's either Google or Outlook.
So you could do what I've done, which is I synced everything because I've got an iPhone, but with architecture school, obviously I had to switch my computer to PC if I didn't want to run boot camp in order to run Rhino. So I'm on a PC. But what I did was I linked all of my iCal calendars to basically my Google Calendar, and then that syncs with anything I use. So I basically made Google my main calendar, and it syncs with iCal. So it also syncs with any other application.
Yeah, I don't keep a Google Calendar anymore.
I think you can sync it with your Gmail account, so you don't actually have to keep it. But
I don't have a Gmail account.
Oh, you don't have a Gmail? You gotta get a Gmail. You got Google Docs, you got Google Drive, you got a lot of file transferring that you cannot do.
But I do those with my Mac email. So.
But can you do them with anybody, no matter what platform they're on, whether they're on a Mac or a PC, or can you only do it successfully with people who have all Macs and iCal?
Yeah, it works with some PC stuff. So I do a lot with the San Diego Green Building Council, and everything we do is through Google Docs. So
I'm gonna recommend. I always ex-computer tech here. Gmail, an @me or an iTunes account, and a Yahoo are 3 emails. You should have at least 3 email accounts. As a person in the world, you should have 3 email accounts because you have to have backups for all of them. And as a functioning within the world of syncing, because Apple is so proprietary, you will not be able to function with other Androids seamlessly unless you're going through something else. So just letting you know. We'll continue to problem.
Thank you. Let's not take up any more class time with this. I really appreciate your advice. So Alethea is having a problem getting on. Get out my phone.
Right, I know her laptop's got some issues, but you can see her through it, and then usually she talks through her phone, but for some reason she can't get her phone to work, so she's having some technical issues.
Yeah, gosh, that sucks. Okay. I'm just gonna go with hopefully I'm just gonna send her a quick message. All right. Okay, recording stuff, tech. Okay, so we caught back up on, we went over Heat Island, a little bit more background information on that. Do you guys have any questions about the Heat Island effect? The concept, terminology, how it affects us? Okay.
Well, I mean, I understand the concept, but essentially what I've seen is that some cities are trying to go to whitewash their pavements to stop this, correct?
There's all sorts of different things that different cities are trying to do. I haven't heard of whitewashing pavement. but white does reflect, and it does help prevent some solar heat gain getting absorbed into the concrete surfaces. That's just one part of the solution. Cool roofs, that's similar to whitewashing, is that they're trying to create roof surfaces that reflect more, that so less solar heat gain is getting absorbed by the building, more of it's reflecting back to the atmosphere. In addition to helping with the island effect, that also helps the building's performance in lowering their actual energy consumption. Other than that, the green roofs, the trees, the vegetation, all of that stuff, bringing more of that into the city is one of the most effective ways to help cool down the air temperature. But I don't think that you're ever going to be able to get rid of it completely. It's just part of what happens when you stick a whole bunch of humans together in a very crowded space. We're just going to be giving off more heat, because even our bodies are, create heat constantly. If you think of,
I guess I had a question about reflective heat, because since obviously right now one of the things we're trying to do is to stop the heat from being absorbed by concrete and staying. So we're putting, like you said, the white roofs. I've seen LA whitewashing some streets to make them reflective. Obviously that reflective heat is going to go somewhere though, and it's going to go above the city. So I guess my next question is, what can we use to absorb the heat instead of just reflect it away? Absorb it and store it and release it when we want it.
That's a really good question.
Last semester, I read an article about something that scientists were experimenting with creating their own clouds and using those clouds to reflect the sunlight back into space. So I don't remember much of it, but it was like an interesting read, saying that those clouds have like different kinds of particles that would absorb that same light.
So like artificial weather clouds.
Yes,
they're doing it in the Great Barrier Reef. They're deploying the technology.
Wow, that's pretty cool. I've not heard of that. I'm gonna look it up.
Mars, didn't we read? Wasn't that a Patrick article?
Yes.
Yeah, it was, wasn't it? Yeah.
It was.
Okay, I'll look that up. Thank you. I haven't heard about that one.
If you want, I can look into my files and see if I can find the article for you.
Yeah, if you can find it, that'd be great. If you can't, I'm sure I can find it with a Google search, even if it's not the exact same article. Tabitha, back to your question about capturing the heat as opposed to just reflecting it back up to the sky. That is one of the strategies for cooling, is to use thermal mass to actually capture that heat, and then try and re-radiate it back at night. So yes, that's another part of the say puzzle, but another technique to add to the kit of tools to deal with the heat island effect.
So we still have room to develop, is what I'm hearing. There's still room to develop ideas for catching heat, absorbing the heat and light, and control dispersing it.
Yes, absolutely. But it's also there's no one solution that's going to work everywhere, and different cities have different climates to begin with, and so it gets more exacerbated in certain climates, like Houston. It's so hot and humid that you know, that's going to react differently than Seattle does, or San Diego for that matter, because we're a lot drier here typically. So each city needs to work on selecting different techniques that will work for them in their given conditions. And yeah, technology is changing, increasing all the time. So what now is almost, some things that are almost commonplace today didn't exist 20 years ago. And so over the, you know, the course of your careers, you're going to see a lot of changes also happen. Okay, moving on. Are we good? All right. So thermodynamics, that's the subject for this week. There's a bunch of different aspects of it. I like to look at how things got started. So thermodynamics started with, or the concept and the study of defining it at the beginning of the Industrial Revolution, when steam started to become used, and in particularly steam engines, and how to increase the efficiency of steam engines. So they were looking at that, but it wasn't until Lord Kelvin, from the Kelvin temperature system was named after him in 1854, where he defined thermodynamics is the subject of the relation of heat to forces acting between contiguous parts of bodies, and the relation of heat to electrical energy. Now, what that is talking about is how heat can travel between different surfaces. What are those methods of how does that work? And then also its relation to energy. So, who knows which building this is? Anyone? No? Nobody knows what building this is? Okay. Welcome to the pseudo history of architecture, history of modern architecture. This is the Glass House by Philip Johnson in New Canaan, Connecticut. Now, it is a pure glass box, flat roof, pretty much not relating to anything to do with the climate. This photo looks like it's from the fall. How do you think it would feel to be inside this building given the fall conditions?
Exposed.
What more time?
Chilly, a little cold.
Chilly? Chilly? Okay. What about now?
Very cold.
Colder.
Freezing. Is there a fireplace in that brick?
I do believe there is a fireplace in the back. This is the bathroom mostly. At this angle, I can't tell. I think there is a fireplace in there.
Still chilly.
Yeah. So, and I bet when this was built, I'm sure this is all single pane glazing too.
How old is this house?
Oh gosh, when was this built?
Because I feel like that's kind of the trending right now, is doing glass houses in the woods.
Yeah. Let me do. This is one advantage actually of doing things virtually. Glass House, Philip Johnson. Philip Johnson, the Glass House. Let's see if I can find a date for it. Except everything else is in my way. Mm-hmm. 1949. So, not early international, but fairly modern. So, the point of showing this example is to start thinking about the transfer of energy from one surface to the next and how that affects our body and therefore our thermal comfort. To define temperature, we use Fahrenheit. When I say degrees, I'm not always going to remember to say Fahrenheit, but that's what I typically defer to because of practicing in the United States. The definition of temperature is the amount or the quantity of heat intensity. So heat is transferred between two different surfaces based on a difference in temperature, or delta T, delta being a difference and T being temperature. The key thing to remember is that we always want to be in equilibrium. Hot is going to migrate towards cold, and cold is going to migrate towards hot until surfaces, objects, air, volume, water, all reaches equilibrium. Two different types of heat definitions that you need to know. Sensible heat is the heat content proportional to dry air. And there's three different methods of heat transfer. There's conduction, convection, and radiation. Sensible heat is what the thermometer in a room, if it says it's 78 degrees, that is reading sensible heat. It is not looking at the humidity or how much moisture is in the air, so therefore the dry heat content. Latent heat is the energy that is required to change the state of the matter from solid to liquid or liquid into vapor. So it is water evaporating. It takes energy to evaporate water. That is heat. That energy is what we define as latent heat. How this is going to affect us, and I'll come back to this, but
this may seem like a dumb question, but is the opposite latent cold? Like, is there?
No.
Okay.
No, and that's not a dumb question. Sensible heat is really easy for most people to understand. Latent heat is a little harder. It's what's needed for a phase change, and where that most directly affects us is with air conditioning. An air conditioner is always removing moisture from the air. It's almost like a dehumidifier, where the as you know, I'm thinking of an example. Most air conditioners, or not most, all air conditioners create condensate. That's that water. That is that moisture that they pull out of the air. The energy required to take that moisture out of the air is the latent heat. That is in addition to the sensible heat that is going to lower the temperature in a space. So this next slide, this is a page out of a Title 24 compliance document. You don't really have to know too much right now, other than this is a load summary. So it's talking about how much energy is needed to either heat or cool this particular residence. It's got several different zones for the different rooms. So for cooling, you need two types, there's two different quantities of energy that affect the cooling load on a space. The first one is the sensible heat. That is the energy required to lower the dry heat contents, to take the temperature from 85 down to 78. The latent heat is the energy required to remove the humidity in the air, the moisture in the air as that temperature comes down. So different, and we'll get more into this on Friday when we're starting to look at the cyclometric chart, but different temperatures of air can hold different quantities of moisture. The higher the air temperature, like 100 degrees, can hold a lot more moisture than dry air, like cold air, like 50 degrees. There is a limit on how much moisture can be in 50-degree air. Has anyone ever spent time in like New England or northern climates? I was raised in New England, my formative younger years. In colder climates, oftentimes in the winter, when you're heating a space, you have to add humidity back into the air because it is so dry. In hot, humid climates like Houston, Texas, is where you want to be dehumidifying and taking moisture out of the air because it's so hot. And that's why they call it relative humidity, because it's relative to what the air temperature is. That's the starting point. Okay, so we've got sensible heat, latent heat. How do we measure that? We measure that in British thermal units, BTUs. That is a quantity of energy, but what we often are talking about is actually the flow of heat energy over a period of time, and that's called BTUs per hour. So how much energy is used per hour? And this drives me absolutely bonkers, but the convention for the flow of heat is BTUH, even though it's over a period of time. So it should be BTUs per hour. It should have a slash here so that you know it's over a period of time, but that's not how they do it in engineering, and it drives me nuts. Because when you start doing calculations and you're following your units, it can get really confusing if you're not remembering that it's over a period of time. And the time that we default to is an hour. Metric system, whole lot easier. It's just plain watts for them. That includes the time factor in it. It's watts are joules per seconds, I believe, but you don't need to know that because that's not how we do it. Okay, key terminology to know is enthalpy. That is the combination of both sensible and latent heat together, and that is measured straight up in the BTUs. So technically it's 1 BTU per pound of dry air. Don't worry about that too much. Just understand that it's not flow of heat, it's just a quantity. So it's like at one given point in time. Okay, and then this is the Title 24 example. So
then all those numbers would be in BTU, correct? Is that the unit for
They
those?
should be, yes. They should be. And it's just BTUs, or is it BTUs per hour? I don't really remember. And I don't know why it doesn't say. The Title 24 compliance documents, sometimes the way they've been set up and established by the state, they're not always remarkably useful, other than proving how your building's performing per the state code. The point of showing you this example, though, is that cooling has the latent heat load because it's removing the moisture. Heating does not have any latent load because by default, typical heating systems do not add moisture back into the air. That's why in cold climates, you might have to have a separate humidification system. Okay, so we were talking about, okay, so there's two big things we're going over here is the type of heat, and now how that heat is transferred. So jumping back to, there's three different methods. We have conduction, convection, and radiation. Before I jump into conduction, at this point in time, do you guys have any other questions on sensible or latent heat? No, not yet. Okay. Been through. Okay. Conduction is when heat is transferred through a solid material. You have to have a temperature differential or a delta T between the two different materials. So between one has to be hotter, one has to be colder in order for the heat transfer to occur. If they're both the same temperature, they're at equilibrium and there is no heat transfer. So it's based on to calculate what conduction is, you need your delta T plus your area of material, and that would be, area is square feet, plus a material conductance, and that is a value that is associated with different materials. And there's different charts where you can look that up. For example, metal conductance, metal is highly conductive, so it is at the high end of conducting versus, let's say, what doesn't conduct very well? Maybe fabric, glass. Glass is not highly conductive either. So there's a range, and every material is a little bit different. So if you're doing a lot of calculations, looking at these things, then you just use the charts and you look it up. And so what that is measured in is BTUs per hour times the area times the delta T, which is in Fahrenheit. So in this case, I typed this in, I put in the divided by sign, but it wouldn't necessarily be there if an engineer was looking at this. Okay, so that's conduction. So it's between two materials. Convection is heat transfer between two different material states, like a surface and an air, or water, which would be a liquid, and I should say not air, I should say gas. Air is technically a gas. So convection is between two different types of materials, or states of materials. Again, it requires a delta T, the temperature difference, and just the surface area. It's no longer looking at the conductance of the materials. It can be done either through forced mechanical energy, such as a fan or a pump. Fan would be between air and like a surface, like a floor surface, like stone or wood. Or a pump would be between water and a surface. And you can think about that in terms of like a pool, the body of water in the center and the sides of the pool. Typically, you want your water warmer than the shell of the pool. So what's happening is the heat wants to transfer from the water to the shell, but by using a pump and adding heat back to it is how you keep your pool temperature up. Same concept for blowing warm air into a room or cool air with a fan. The fan is forcing the air to circulate, and as it moves, it passes over the surface. And if the surface is colder, it will absorb heat, and if the surface is warmer, it will give, I'm explaining that right. So if you blow hot air over a cold surface, it will heat it up. If you blow cold air over a warm surface, it will cool it down. You can also create natural convection, and that is done strictly based on temperature difference. So an example of that is where, okay, you're not forcing any air to circulate in the room, but if you have a floor surface, and this is like passive solar heating. Floor surface is really nice and warm because it's been collecting a lot of solar heat gain during the day. It warms up, but your air is cold. The air next to the warm surface is going to warm up, and the warm air will rise, and it will create a natural convection, and cold air will fall down and come along the surface and warm up. So it creates the natural convection. It doesn't work nearly as fast as a forced air, but it can work really well. So conduction, convection, air. Key thing to remember is that air is the best way to insulate, to create insulation, because it does not transfer heat well, because the molecules are really far apart and it has an incredibly low conductance value. So air is used as a form of insulation. And so we were talking about how the conduction is based on temperature difference, surface area, and the material. So the heat transfer across an airspace is dependent on the distance between the surfaces, the area of the surface, and the smoothness of the surface. It's not the same thing as conductance, but it's a measure of the quality of the material. Fiberglass bat insulation, it's very, very lightweight. It's fiberglass that's strung out into very small strands with a lot of air trapped in it. So the material is very low, the fiberglass is very low in quantity, and there's a lot of air in it. And it's really important when you install fiberglass insulation that you don't squish it, because what that does is it pushes the air out, and the insulating value of that insulation will go down, because you're decreasing the distance. Rigid insulation, which is typically a polystyrene or styrofoam or a material like that, is made up of lots of little tiny circles of a material, plastic, poly something, that is enclosing little air bubbles. And so again, the amount of material of the poly product is low in quantity, but it's entrapping a lot of little tiny air bubbles in it. And that air is what's the insulating value. Now, the reason rigid insulation has a higher insulating value per thickness than batt insulation is because with all those bubbles, it's really increased the amount of surface area of that poly material. So there's a lot of surface area in relation to the air, unlike batt insulation where it's strands of material with air flowing in between. And then also, so with the rigid insulation, when the area is, it's really, really small. So even though the distance is little, the air can't flow as much in those little tiny bubbles. And so it lowers that natural convection that's going on. So high surface area, volume of air, but there's not enough space because the bubbles are so tiny that it's not getting any convection going on inside of it. All of these different factors are making up why it works as an insulation material. Which is what the last bullet point is talking about. So these different methods of conduction and convection, and how they work between materials, material surfaces, the distance, the volumes, all of those things come together to determine how well that insulation is going to be working. Air being an insulator is also why in double pane, like glazing, double pane glazing always has an airspace or a gas. Some of them have argon inside of them. It's because by putting that air gap in there, you're essentially adding insulation. If you just took two pieces of glass and laminated them together, they would not perform the same as an insulated glazing unit. Okay, whoops. Air, convection. Okay, a couple different things that happen with convection to keep in mind. Infiltration versus ventilation. You want ventilation, you don't want infiltration. So ventilation is planned airflow. Infiltration is unplanned or unintended. And airflow is measured in cubic feet per minute, CFM. We jump back to our little Title 24 compliance document. In a typical way that we heat and cool our spaces is through forced air convection. And so the the compliance documents also quantify what volume of controlled airflow you need for you to meet your loads. And typically it's directly in relationship to what the overall load is. So for this cooling load, this master bedroom, the heating load or the cooling load is extremely high, and it needs more airflow at the peak cooling time, which is August 3rd here, versus this bedroom down here, bedroom number 3, very low cooling load, a lot less airflow needed with your typical forced air system. Okay, the third method is radiation. Conduction and convection are fairly straightforward. Radiation is the most challenging concept for heat transfer. And it is related to the electromagnetic waves, which is energy, and how it radiates or emanates from a warmer material to either another material, which could be solid or could be a gas. It is dependent on line of sight. So you can't, it will not go through materials or surfaces. If you're radiating out and it hits a surface, then it becomes conduction, because then that surface would be the next material to transfer it to the following either material or space. The easiest example to think of for radiation is a fireplace or a campfire. You stand, the closer you stand towards it, closer you stand to it, the more you will feel that energy that is being radiated from the hot source. Solar, the energy that we get from the sun is radiation. And it comes from the sun, it hits our earth, it hits our atmosphere, and then a couple things happen. It's either reflected back out, it's absorbed by the material that it hits. That could be clouds, it could be ground surface, it could be building, it could be a body of water, or it's transmitted through a transparent material such as glass. It cannot transmit through a solid material, an opaque surface, such as a block wall or a wood wall. And the other thing to remember is that radiation can travel through a vacuum. It is not dependent on having a gas or to flow through, vacuum of space. There's no material there that radiation is moving through. It just, it moves straight through a vacuum until it hits something. And in our case, it hits the earth, which has our atmosphere, which is a gas or layers of gas and multiple different ones. And then it comes through there, or it is reflected and it hits our clouds, our weather systems, and then a surface somewhere. So the earth is opaque, and so the radiation is not going all the way through the earth. Okay, so a couple of examples here of, I'm just gonna skip this. I'm gonna take that slide out, don't worry about it. It's from the old textbook. I'd rather not focus on that. But what I do wanna show you is the the electromagnetic spectrum with all of our different types of essentially energy or radiation. The visible light range, which is the human visible light range, has our spectrum of the rainbow, so red, yellow, orange, green, blue, purple, violet, and then this is what the human eye can see. If you are getting smaller, the wavelengths they go to ultraviolet, then to X-rays, gamma rays, and then maximum X-rays. If you keep in mind, X-rays can travel through solid surfaces. So the easiest way to remember that is Superman's amazing X-ray vision. Humor, smile, laugh, crackle, something. Okay, easy way to remember it, okay? Going back to our chart. So those are where the wavelengths are getting smaller and smaller and smaller. And so the X-rays are the ones that can go through surfaces. In the opposite direction, you start to get the warmer and the hotter energy wavelengths. So above the visible spectrum, you get into the infrared. There's infrared cameras or night vision goggles that can read what that energy is and convert it into a graphic that we can see within our visible spectrum. And then as you get hotter and hotter, you get into the microwave range. So shiny or mirrored surfaces reflect visible light, and because they're opaque, they also reflect radiant heat. If you guys think of those 1970s office buildings that are completely covered in mirrored glass, that was the early form of, well, other than being a really bad architectural style, it was also an early form of high performance glass by making it completely reflective to keep out the solar radiation so that it doesn't transfer through the glass and land inside the building and heat it up. Okay, we went through Superman. Okay, so we talked about our two kinds of heat, sensible and latent. We talked about our three methods of heat transfer: convection, conduction, and radiation. A couple more concepts. We lightly touched on evaporation last week when we were talking about climate. This is not a method of heat transfer, but it is a cooling mechanism because of the removal of the latent heat from materials, or from the pulling moisture out of the air. So as the temperature rises in the atmosphere, we start absorbing more heat from around us, and the way that our body can feel cooler is through evaporation, also known as perspiration for humans, which is why evapotranspiration makes us feel cooler if we're feeling moisture being evaporating off of us or from around us. Here's a little a story or experience that I went through that might help you understand if you haven't felt this before, or this might make you remember another time where this felt similar. So I spent a lot of time in Japan studying architecture and art, and I have a bunch of good friends there. And I was with a friend once, and we went to her this city festival that they have in the summer. And the festival was where they took water in little buckets and ladles, and then part of the festival was where everyone went around sprinkling the water all over the ground. And at first I was just like, why? Why are we doing this? But it was summertime, and about 10 minutes into this, because Japan gets really hot and humid in the summer, the air temperature started cooling down because the water that we had been sprinkling on the ground, which happened to be concrete for where this was being held, started evaporating. And you could feel the evaporation going on around us, and it created the cooling sensation. And so you started to cool down and feel better. I've heard other people talk about a guy I knew was Greek, and he said his grandmother would always go out and sprinkle water in their courtyard in the morning, and that helped keep the courtyard cool during the day. So this is how I remember that evapotranspiration is the cooling mechanism and how it makes the body feel, and it's a sense that we feel. Evaporation is dependent on the saturation level in the air and on air movement. Keep that in mind, though. Okay, that was my little story. So taking our types of heat and our heat transfer methods is the first part of understanding the thermodynamics of buildings. And there's 2 laws that you need to be familiar with. The first law of thermodynamics is that energy can neither be created nor destroyed. And this is similar to equilibrium, that heat is always wants to become equal. So heat is going to flow from hot to cold or from cold to hot. And it's not going to disappear. It's going to be in one form or the other, or it's going to be lost into the air as, I shouldn't say lost, it could be transferred into the air through convection. The second law of thermodynamics, and this one's a little bit harder to understand, but the second law is that as time passes, the energy will tend towards a lower and lower quality. Okay, but how do you define what quality of energy is? It is defined by the form and temperature. So form being a material, a solid material, or a gas material, or a water material, and its temperature. So if we go back to our pool example, where we have a pool shell and a body of water in the center, that you've heated up the water and it's now warmer than the shell of the pool, but you turn off the heater. So that body of water is, that heat is going to transfer through conduction into the shell of the pool. But if you were to quantify and measure the absolute amount of heat that leaves, that's the temperature of the water and goes into the shell, it's never going to be exactly 100%, because there are going to be minor effects, that there's going to be some evaporation, You're going to lose heat through various different forms. If you're talking about air within a room, there's micro infiltration. You open a door, you open a window, you lose a little bit of heat energy. So the energy is going to get, it's lazy. It's going to do the easiest thing it can do, which is either be conducted or convected into an immediate other source, or a form, or another material, or another state like gas or water. But it's, and this is why it's kind of a little bit harder concept to understand, but it's just gonna keep going to where it's easiest. So it's gonna tend towards a lower and lower quality, but at the same time, it can neither be created nor destroyed.
Is that how is that second law affected when you consider things like hydrocarbons being refined, like when you take oil and change it into gas? Is that law affected?
I don't think so. I don't know a lot about manufacturing and refinement of hydrocarbons, but there's always going to be losses somewhere along the chain. The way that I can think about it the easiest is the concept of air in a room, is that you can build, the biggest, most insulated box you can to keep your temperature inside. But even, there's no doors, no windows, you think it's solid, you think it's going to stay warm inside, but say over 100 years, it's not. There's going to be some loss somewhere that goes somehow. So it's the energy I get it, and loss is not the right word. It's that heat is energy, and that energy is going to go somewhere. And it can be microscopic in the way that the heat leaves to become a different form, either hot or cold, or transfer somewhere. But it's also lazy. It's always going to take like the easiest way out. So I don't know if that addressed your hydrocarbon question quite so much. I'm sure that in the manufacturing, they're changing the material, but it's going somewhere. It's either becoming another material, or lost through heat or cold, or whatever that manufacturing process is, or it's conducted into
you probably have to take into account the electricity that goes into refining the.
Well, so you're adding energy in, and you're using that energy to manipulate something, and therefore you're going to get something out of it. You're using that energy to change the state, change the form, break down the molecules, whatever it might be. But that energy just becomes it just gets changed. Materials are, okay, this is starting to get into theoretical physics here, but materials are really just energy too, but they're trapped, the energy is trapped in the molecules and all of the molecular structure that's binding it together. So if you think of the sun is basically one giant nuclear fission bomb that's made up of hydrogen, and as it's burning and giving off all the solar radiation that the Earth gets to absorb, it's slowly changing the nature of the interior of the sun. And when that fuel, the hydrogen, gets used up, in 3 billion years or whatever it is, sorry, I dropped my earbud, the sun will go supernova or whatever it does in its next life form. All right. Well, I've got one earbud left. Sorry if I can't explain the physics aspect. That's not really my specialty, but what is important and what's important in this class is to think about what is temperature, what is heat, how does it move from one place to the other, and why this is important is because it affects our buildings. So first class, we talked about building mass and its orientation to the sun. So we have that radiation. So we talked about radiation, which is a form of heat transfer, that our building and our building mass is being affected by that radiation. And so understanding how that's affecting us is the key concept here that I want you guys to walk away with, understanding and cognizant of when you're shaping a building and how you're locating that on your site. And there is no good, bad, there is no right and wrong. There's just choices and decisions that we make as designers. And as we're choosing to put materials in our building like glass or insulation, or how we shape the room for better natural convection, understanding how the energy is going to move and how it's going to be affected by these different surfaces and how insulation works. These are all this is the background information that I want you to understand, so that when you're making these choices, when you're designing your buildings and you're choosing what to put where, you know how that's going to affect the thermal comfort of your design. Don't get too caught up in the laws of thermodynamics. That's not the knowing that they exist is good. Understanding the theoretical background of it is not the purpose of this class. This class is just to learn about how our buildings perform and the things that affect them. Okay, so sensible heat, latent heat, and the 3 methods of heat transfer. That's the core gist of today. And on Friday, we're going to start looking at the psychrometric chart, which is looking at temperature and humidity and thermal comfort. And we're going to do a couple little heat transfer exercises. And that's it for today. That's the end of this lecture. Tabitha, if you can hang out for a minute, that would be great. Does anyone have any questions? Okay, don't forget, I've put the first assignment up. It's just a fill in the blank. It's one sheet. I think it's 10, 12 questions or so. And it's due on Friday. If you haven't read chapter 4 yet, or 3, please take a look at them before Friday. And that's it. Unless you guys have any questions, you want to hang out? Thank you. Okay.
Alrighty.
Hey, I'm going to just copy the chat before I lose it. Copy, because it's got that web link in it.
So I was actually just going to recommend that since we're on Rain Central, you can share your screen with me and open up your Finder window, and then we can kind of like go through the Finder window together. And if you need to change the properties to see the address bar, then I can help you with that.
Okay. What's going on here? Copy, command, copy. Why can't I copy this? All right, let me do this. Stop share and pick my other window. Desktop 1. Share. Okay.
Go ahead and open up a Finder window. All right, it looks.
Are you seeing that?
Yes.
Okay.
So, yeah, you don't have your address bar. So right click on that where you are right now with your mouse. Shoot, it's not there. Ah, there it is. There's little settings gear actually. Go ahead and hit the drop down. They always changed it, so I always want to have to see what their new stuff is.
Yeah.
The gear itself, and not the drop down of it. And I think it might open up a preference window. No, it shouldn't. Go ahead and scroll down. See, show preview. Show preview options or view options. Yeah, view options. Show view options.
Let's try show.
Yeah. I wonder if you can like. Oh, there we go.
It says documents.
Great. So where you see preview options, the preview options window, where from? Hit the click where, hit the general, click general, and then click where from. Basically, this is gonna, I think this will help you search for things when you select a file. So like right now you have assignment number 1 selected. It's supposed to basically show you the, go backwards. You have it on list right now though, so it actually might work that way. Can you go to your downloads file actually just to see if it's in there? You can close those other windows I had you open up. Now that you general in there.
So here's downloads.
It's not there.
I was wondering if it might go to my desktop.
Central, is there a Ring Central? I'm Google searching right now how you can find it on a Mac. Users, okay, so I think this is it right here. Documents and Ring Central meetings. Can you go to your documents folder and see if you have a folder in your Finder window? Or you must have taken it off of your, there you go. Do you have a Ring Central? There it is, Ring Central.
Yes.
Meetings.
Yes.
There's the recording. And so if you go into each one, they have the audio and the playback. There you go. Perfect. So
Awesome.
I'm going to go to that file every single time you record. So for me, I have a dual hard drive, and where it saves it, it doesn't have a lot of space. So I pretty much pull it and put it into like my school file every time I save it, just so that I don't have it there. But you can leave them there, and they're all just going to file there, and they're going to have the date on it, just like that on the file name.
Yeah. And I can upload this to Moodle.
Exactly. So now you have the MP4. So you can just upload the MP4 straight to Moodle.
Is this one important? The M3U?
So leave them with the files, but when you shouldn't have to select those. But those are kind of like system
stuff.
files, basically, for the system to know like what goes where within the file itself.
Okay. Probably the best thing to do is just upload the whole folder so that all 3 of them are there together.
Why not let you actually? So go to YouTube. It's going to ask you to select an MP4 file to upload or a video file. You can put different kinds. Video files can be different things. It can be not MP4. They can be VHA, or they can be a bunch of different like point whatever. But that's an MP4, so you'll be able to select the MP4, and it should just work automatically.
Just looking to see if there's a easy thing to upload here.
To be honest, I'm going to tell you, it might be easier for you to create a YouTube account.
Okay.
Upload the videos to YouTube, and you can make them all private so that nobody can like search it and everything. And then you can just load the link in so we can look at the YouTube link. But I don't know if that's going to be too much. But I don't think that that Moodle lets you upload direct MP4s to it, it lets you put links to where the file is on a server for you to look at. So like YouTube or iTunes,
Okay.
some other server where they.
I can play around with Moodle, so.
Yeah.
All right.
But if not, to be honest, like a really fast thing is if you don't have a YouTube account, the YouTube account's really easy to log into and upload MP4s, and then just copy and paste the link to Moodle, and that's really fast.
Okay.
But I'm glad you found them. Do you have any other questions for me? Well, you got me?
I don't think so. Thank you so much for your help.
Not a problem.
I didn't see that.
It's all good.
All right, cool. You too, and I will see you on Friday.
Yes. All right, bye-bye.
Okay.